Okay, so as today we'll do homework. Um, Still on Markov chains. I think the problems are a little more interesting this time, a little harder. Um, and yeah, I guess the big test is coming up on Thursday. Hope everyone is feeling good about that. Shouldn't be too hard. And yeah, let's start. So. Start with the first problem. Okay, so we have a Markov chain. Now let A be, a set of states. In other words, A is a subset of S, and let's also consider its complement, which is also a set of states. S, and the union of the two is equal to the state space itself. Let's see. So for part A, we're given this double sum. So sum of I belonging to A, J belonging to A complement. Yeah, Pi times Pij. Okay. So and we want to find just a way to interpret this. So before we actually say what this is, what would this be? Well, we know that this is the long-term probability of being in state I, and we know that this is the probability of transitioning from state I to J. So we can interpret this as the long-run sort of rate of going from I to J. So given this fact, then how do we interpret this? Well, we're adding essentially the long-run rates of transitioning from states in A to states in A complement. So this would just be long-run rate of going from A to A complement, because we're just adding these individual rates for all the states that originate in A and that go to A complement. And then similarly, the same thing applies for B. This is just, let's say, long-run rate of going from A complement to A. And now the interesting part of the problem is part C. Where we want to explain the following identity. So we want to say why these two are essentially equal. Okay, so why is this true? Well, a sort of an intuitive explanation would be to say that the long-run rate of going from A to A complement would have to be equal to the long-run rate of going from A complement to A. And why is that? Because for any transition that we make from A to A complement, then in order to make another such transition, we have to go from A complement to A, right? So for any transition from A to A complement, again, in the long run, in time plus infinity, we will have to have made a transition from A complement to A, because we need to return to A. So that's kind of the intuitive explanation of why this identity is true. It's not done in the solutions, but we could also very easily kind of show this with a math. And I'm going to go through this kind of quickly. So let's see. So in order to derive this, first of all, I'm going to use this notation here. So this means the double sum for all ij, but now we're taking ij such that both I and j can be any state in the state space. Okay? Okay. So now if we were to, actually before we do that, and maybe this notation is not so good now, but let's do this. So let's see what this would add up to. Okay. So this is a double summation. And we know that since everything is positive, I mean, this could be an infinite summation. There could be an infinite amount of states. But since everything here is positive, there is what's called the Tonelli's theorem, which allows us to switch the order of summation. I mean, note that we could always do this if we had a finite sum, but this could be infinite. But in any case, we're fine. So let's switch the order of summation here. And see what we get. Well, okay. So this would be the sum over all j. And now, what is this term here? This is this reminds you of something, right? This is pi j. So, and then we add it over all j. So this will just give us 1. It's pretty clear. Okay, so we know that this is equal to 1. Now, let's find another way to rewrite this that would involve these two sums. Because that's ultimately, we want to prove that they're equal. So, okay. Well, so we're taking all pairs that belong, so it's like that belong in SS, or in S cross S, right? So we can partition now S cross S into 4 different components according to what A is. So we can then say that this is the sum, Pij, where Ij now belongs to, say, AA, plus the sum, and I guess we're always summing this term, so I'm going to omit it from now. I mean, you'll see why, but it's the same sum here, but now where Ij is from A, where I belongs to A and J belongs to A complement. And we're essentially here, we're dividing into the 4 quadrants. So A complement A of the same term plus this sum and we know that all this we just proved has to equal 1. Okay. Okay, So now, given this information, let's try and calculate what this sum is, and hopefully see that it is equal to this one. So the sum ij belonging to a complement. Okay. Now we use this equation here. So A and A complement would be just 1 minus the three other sums. So it's 1 minus this sum. And here I'll omit the ij. I'm being very lazy, but I think you get the picture. Minus this sum now from A complement to A, minus the sum from A complement to A complement. Okay. Okay, so let's see what we get. Well, we see that if we add these two sums, what are we going to get? Well, we'd be summing now over I that belongs to A and to A complement. So we're summing over the whole state space in terms of I. So we're summing now, say, S to A of this term. And we also need to subtract A complement and A complement. Ieorertsj. Okay? Okay. So now, sort of the final trick that we need to do is to express this in a different way, to express 1 in a different way. So you see why this is equal to 1? Because again, now we're taking all the different possibilities for I and for j. And let's continue subtracting the other two terms. Oops. Okay. So, you get some cancellations here. Oops. Wait. Did I make a mistake? Oh, shit. Um, well, okay. So I didn't justify something in the little proof that I wrote, which is that these two terms are equal. So we can cancel them. I didn't justify that because I made a mistake with the sort of SA and AS. But provided that we can do that, and I think we can, then we get the difference of these terms. Okay, so now we would be summing over I that belongs to A complement, and now we can take J to belong either to all of S and then belonging only to A complement. So in the end, we'd be left with a double sum where now I and J belong to A complement and A, which is what we wanted to prove. But we need to justify this step here. I wouldn't really want to improvise right now, but I think I mean I can do it. I can look at it after recitation, and if someone is curious, please come up and talk to me. Yeah. So that's sort of another way to explain that final part of the problem. Instead of just being intuitive about it, we can mathematically derive it. So now let's move on. You don't need to write this, but just want to check something. Oh. Okay, yeah. Oops. Anyway. Okay. Yeah, okay, so the mystery is solved. So why are these two terms equal? Okay, so just a quick note. So sum of I belonging to A and J belonging to S of this term here, well, what is this going to be? We can take the pi I out of this summation because we're only summing over J. So we're summing over all J here. And because it's a Markov chain, this has to sum to 1. So this is equal to the sum over I belonging to A of pi I times 1. So this is the sum of pi I where I belongs to A. So this is what the first sum gives us. Now let's see what the other one does. That's Pij. Well, now what we do here, we change the order of summation again, which we know we can do because the terms are non-negative. So we do this trick here, and we know that since these are the limiting probabilities, this is just pi j, right? So this is the sum, now j belonging to I of pi j, and these two are equal. Sorry, I was unprepared there. But you see why those two are equal now. So that's why we can just cancel out this and that. Okay, so enough of that problem. Okay, let's move on to problem 46 now. Okay. So an individual possesses R umbrellas, which he employs in going from his home to his office and vice versa. If he is at home or at the office at the beginning or at the end of a day and it is raining, then he will take an umbrella with him to the office, home, provided there is one to be taken. If it is not raining, then he never takes an umbrella. So assuming that independent of the past it rains with probability P, then we need to do the following things. So we need to define a Markov chain with R plus 1 states, which will help us to determine the proportion of time that our man gets wet. Okay. So it rains probability P. So we have R umbrellas. Probability of rain is P. And the guy takes an umbrella if he's at the office or the home and it is raining. So I guess the most important thing here is to find a way to define a good state space for our problem. And so we can define the state to be the number of umbrellas at present location. So it could either be the home or the office. And this is a really good way to look at it because we can readily sort of determine the transition matrix, the probability transition matrix. So what would this probability be? I guess, and also this can go from 1 all the way to R. Okay, so if there are no umbrellas at the guy's present location, well, there's none to take. So at his next location, there will be R umbrellas there. So that's pretty self-explanatory why this would be 1. Okay, now let's see. Now, say that there are I umbrellas in his current location, which means there are R minus I in the other location. So when would this be the same? So in other words, if there are I now, when would he not take an umbrella? And therefore still have I in the location that he is at now, and R minus I location where he's going? Well, it would be if it's not raining, right? So this would be the probability that it is not raining now, which is 1 minus p. And similarly, say that he has I umbrellas, and he takes the umbrella. So therefore he has R minus I plus 1 umbrellas at his next location. Well, that will happen with probability p, right? It is the probability of raining. So actually, yeah. And this is all we need to do to yes?
In the third case, if you start with I umbrellas in the office, let's say, when you take one, where you end up with I minus 1.
Okay, so the question was, if you start with I umbrellas in your present location and you take one, why don't you end up with I minus 1? Well, yeah, I mean, you definitely do, but now you have changed locations, right? So, and remember that you define the state as the number of umbrellas at the present location. So when you go to the different location, at that different location, you will have one more umbrella than what you previously had. Yes?
Another way of looking at it is that R minus I plus 1 term is going to become your new I, so that
yeah, exactly.
R minus I term is going to take that into account.
Yeah, exactly. So yeah, the observation was that this new R minus I plus 1 term becomes the new I, so to speak, because this becomes your new present location. So yeah, it's a little confusing at first, but the whole trick is to just really understand what the state is. And this problem would be really hard to do if we didn't have this clever way of defining the state space. So, everyone's okay with this? Okay. Now let's do, so we want to show now the following. Actually, right near this. So, show that okay. So we want to show, in other words, that the limiting probability of having, a certain amount of umbrellas at the current location is given by these formulas. So what do we need to check? Well, first of all, we know that by the theorem that since this is a irreducible aperiodic positive recurrent chain, there will be a unique solution. No, there will be a unique stationary probability distribution. So now, which will have to satisfy the two conditions. Remember, the P transpose P equals P transpose, and that, of course, for it to be a probability, it has to add up to 1. And of course, it has to be non-negative, but that goes without saying. So this condition is very very easily verified, right? Because we have R of these states. So if we sum up all of these probabilities, would be R over R plus Q, and we add Q to it, so it adds up to 1. So this is fine. So now we need to check this condition here. Okay. So, another way to write this P transpose thing is that pi j is equal to the sum over all I of, so I guess here I ranges from 0 to r, pi I times pij. And now, remember what the matrix P is. So, if we were to write these equations, let's see. So what is pi r? So pi r would be just pi 0 times 1 times p0r, which means 1, plus plus p1 times p. Yeah. So this would be equal to pi 0 times 1, therefore pi 0 plus p1 times p. And this we can directly see from these equations here, right? Because for 0, p0r is 1, and then when we substitute I equals 1 here, we get 1, r minus 1 plus 1, this is r, and that's how we get p1r. Okay, and then we can do this then for any other state. So let's now restrict our attention to states from between 1 and r minus 1. So here we have two possibilities. So we can either go, so we can go to state j, right? If we are in state r minus j and it doesn't rain, and this corresponds to this term here. Or we can go to it if we have r minus j plus 1 umbrellas wherever we are, and it does rain, and and it does rain, and then we get j umbrellas. Yeah, because if we have r minus j plus 1, then that means we have j minus 1 in the other location, so it rains, we get one umbrella, and we have j. Yes?
So where does that pi j come from?
This pi j? It comes from this formula, and from the fact that we can only transition into state j, either from state r minus j, in which case, pi of r minus j is equal to 1 minus p, or we can transition into state j from state r minus j plus 1, and then we go from that state to state j with probability p, with probability of raining, right? So that's where we get these equations here. And finally, so this is for j between 1 and r minus 1. And then for pi 0, we can go to state 0 only if we have r umbrellas in the other state and it doesn't rain. So this would be pi r times 1 minus p. I guess here they're using q and 1 minus p interchangeably. Might be a little confusing. So we need to verify that this guess for the pi i's satisfies these equations. And the truth is that it does satisfy them, and you can check it. It's not so hard to check. So this choice of pi satisfies these equations. So, any questions about this? Okay. So what's part 3? What fraction of time does our man get wet? So what's the proportion of time Okay. So, well, when does our man actually do get wet? Or does get wet? Do or well, when does he get wet? So it has to be a scenario where there are no umbrellas in his present location and it is raining, right? So we have to have no umbrellas and it has to rain. So this probability, so this will be equal to the long run probability of him having no umbrellas where he is times the probability that it rains. And of course we can now just substitute what we have for pi 0. So pi 0 is 1 minus p divided by r plus 1 minus p times, and we multiply this times p. Okay. And finally, when r equals 3, what value of p maximizes the fraction of time he gets wet? So this is just calculus, right? Because if r is equal to 3, then this probability, then pi 0 times p will just be equal to 1 minus p over 4 minus p times p. And now we take the derivative with respect to p. So differentiate with respect to p. So d by dp of this fraction. And I guess I'll take Professor Witt's word that this is equal to pi squared minus 8p plus 4 divided by 4 minus p squared. And now we set it equal to 0. So we set this equal to 0, set to 0. And we solve for p and get p is equal to 8 minus 48 by 2, which is roughly equal to 0.55. And I guess if we take the second derivative, we'll be able to just verify that this indeed is a maximum and not a minimum. So we can do that if we want to. But yeah. Oh, sorry. So yes.
Can you explain how you get pi naught factor or pi 0, where it's 1 minus p over r plus
How I got it? Well, because I mean it's given to us in the problem, right? It says verify that those numbers are the actual. I mean, you could have solved those equations and derived. Yes.
That's my next question, actually. Would it be easy to do that?
What's that?
Would it be easy to do that?
Yeah, I mean, always solving linear equations, especially for a lot of them, and there's no clear pattern, it would be a little hard. But I think that most of the time when you have something like that, you're basically told to verify that something satisfies those equations.
So to finish that off, you just plug in like your pi r and check to make sure that it's pi 0.
Yeah, exactly. So, for example, our guess for pi 0 is that it's equal to q over r plus q. So, and our guess for r is that it's equal to 1 over r plus q. This is q, so this is okay. And I guess you would do that for every single equation here. But the point of this is not to make you kind of solve a difficult recursion to find a general formula for something. It's just know what the concept is, and know to apply that formula and find the matrix. Okay. So any other questions? Okay. So now let's do problem 49. Okay. So let P1 and P2 denote different matrices for ergodic Markov chains having the same state space. Okay. So we have matrices P1 and P2. And these, we have the corresponding stationary distributions, pi1 and pi2. And now consider a process defined as follows. So it's part 1. So x0 is equal to 1. And then a coin is flipped, and if it comes up heads, then the remaining states, x1, x2, and so forth, are obtained from P1. If it comes up tails, then the remaining states come from matrix P2. So if we get heads, then we follow P1. And if we get tails, then we follow P2. Okay? And now the question here is Xn a Markov chain? And also, what is the limit probability, Xn is equal to I as n goes to infinity? Okay, so do you think that this is a Markov chain? Remember the two properties, right? That the future only depends on the present and not on the past history, and that the probabilities are constant over time of transitioning into different states. Yes?
The only question I have with that logic is, like, couldn't you turn it into a Markov chain, but the same way we turned the range problem into a Markov chain, where, like, yeah, it depended upon the previous states, like, range, like, you define the states, so then you have, like, heads or tails would be the first part of the state, and the second part of the state would be whatever, like going from state 1 to state 2. So like the probability of going from an H state to a T state would always be 0, but then you can go from H1 to H2, H1 to H3, H1 to H4.
Yeah, that's a good question. So the question is that couldn't we, okay, so we all know that this is not a Markov chain. We've all seen the solution. But the question is, could this be made into a Markov chain in much the same way as we transformed the rain problem into one? And first of all, the heads or tails thing is not a part of the process, right? Because we just flip a coin basically at time 0. And based on that information, then we either follow P1 and P2. So, and then Xn is not like heads or tails. It's just integers or something else, you know? And I would say that this could be a Markov chain, but only if we somehow kept track of what happened on that fatal flip on the first day.
That's what I'm saying though. It's like, because this says that they have the same state space.
Well, yeah, they do have the same state space. But, so for example, say that if we were to consider the process, say yn, where and yn now is a vector, okay? So yn, the first component of it is xn, so whatever the process does at time n. And then we sort of fix whatever happened at time 1. So an outcome of the flip. Let's say that z is the outcome of the flip. So outcome of initial flip. Let's call this Zn, but let's say that Zn is equal to Z1 for all n. So then it would be a Markov chain. But only then.
If you set it up as 3 states where and you had a set initial state where the first state was that flip and then
Yeah.
that was a transient state that put you into either
No.
over state or another.
No, watch out. The question is if we could set it up into 3 states and first one being a transient state. Well, the thing is that now this is a state. This whole vector is a state. We're not adding, we're just increasing the dimension of the state to capture whatever happens at the beginning, which is important. So that's kind of, yeah. But what they're asking is xn by itself a Markov chain? And that it is not, because we need to know what happened in that first flip. So we need to have this prior history. Yes?
Just to clarify, so let's say just pretend that both states there are just only 3 possible values, 1, 2, and 3.
Yes.
So you have like these states H1, H2, H3, T1, T2, T3, and then have that going like on both columns, and would that be a Markov chain?
Well, no, because what would your matrix? So the question is, if we had, say that xn is very simple and can only say that the state space can only take values 1, 2, and 3, and if we just considered the probability transition matrix of 1, 2, 3, 1, 2, 3, would that be a Markov chain? Well, the answer is no, because we need to know which one of these matrices is our matrix.
That's what I say with the T1, T2, T3, H1, H2, the H and the T capture the first state, they capture the initial roll.
Oh, yeah. Okay, so if we somehow, incorporated this extra information in the beginning, which of course is kind of weird because it's unchanging over time, right? We say, we have the flip, and then in all later sort of time instances, that is unchanged. But yeah, if we could include that, so increase the dimension of the state space, then yeah, it would be. But actually, no, because no, yeah, it would be, of course, it would be. But then we would have, we would have, how many states would we have? We have 3 states, so so our dimension now is 5, so we'd have 5, so we'd have like 25 entries in this matrix. Okay. So this is not a Markov chain. We all agree. Because the Markov property does not hold. Okay. However, we can still figure out what this limiting probability is. But we can figure this out by just conditioning on what happens on that first flip of the coin. So this is pi I. So actually, and since this is an ergodic chain, we know that this limit exists and it's equal to pi I. So this would be pi 1 I with times probability. This is p. Probability of getting heads is equal to p. So times p plus pi 2I times 1 minus p. So any questions? Okay. So now let's do part 2. So now we have this new process, so x0 is equal to 1. And in each stage now a coin is flipped. If it comes up heads, then the next state is chosen according to, so at each so if we get heads, then follow P2, P1, I'm sorry. And if we get tails, then we follow P2. Okay? So is this a Markov chain now? So, let's see. Well, I think that it is, right? Because the two major properties are satisfied. One of which is the Markov property, so the future only depends on the present, not on the past. And also that these probabilities are stationary over time. So let's see what would Pij be? Well, this would be probability of going from I to j. But now we need to condition on what happens on the flip of day n, right? So this is probability, let's write it, so this one given xn is equal to I, and the flip is heads, plus the equivalent thing for when the flip is tails. So we know that this is equal to Pij1, probability heads is just P, plus the other is equal to Pij2 times probability 1 minus P. So this is a Markov chain, and these are the transition probabilities. So any questions? Oops. Okay. So it's clear to everyone why in the first case we don't have a Markov chain, but in the second case, xn, the process is in fact a Markov chain? Okay, so we can move on then. Oh yeah, and in the previous example, I think I said that there are 25 entries. Well, it wouldn't be 25, it would be 18, I guess. Because it's either heads or tails, so. Okay. Okay, so now some gambler's ruin problems. So, problem 459. No, 456. Aye. So suppose that on each play of the game, the gambler either wins one probability P or loses one probability 1 minus P. The gambler continues betting until she or he is either winning N or losing M. Okay. So probability of winning is P. It's 1 minus probability of losing. And the game ends when gambler either wins, say, N dollars, or loses M. And we're assuming that he starts with nothing. Okay? So this is a direct sort of application of the gambler's ruin problem, right? Because, so recall gambler's ruin. Where you know that we derive the following. Did you do this in class with Professor Witt? Gambler's ruin? No? Well, it's in the, I think it's in section 4.5. It's the first application. So, chapter. So, yeah. Over. So let me explain then quickly. So So PI, so say that you have a gambler and he wins or loses $1, or he wins $1 with probability P and loses $1 with probability 1 minus P. And we want to calculate the probability of him starting from some initial fortune I of either reaching a fortune capital N, or we want to calculate the probability that he reaches the fortune capital N before he goes broke. So in other words, that he reaches N dollars, or he reaches capital N dollars, so he wins N minus I dollars before losing I dollars. So this is probability of reaching N before 0, I guess. And this is all in dollars. Starting with, I guess, given that we start with I. This is all in terms of dollars. So we can also view this, very nicely as sort of like a random walk type example, right? So here's point 0, and say this is I, and this is N. And we know that with probability P, we either win $1 and we go to I plus 1, or we lose $1 and go to I minus 1 with probability Q, 1 minus P. So we literally want to figure out what is the probability of this, we can call it a particle or something, reaching point N before it reaches 0. And if you look at the analysis that's done in the book, pretty straightforward derivation gives you this formula here, which also it makes a whole lot of sense, right? For example, say that you go left or right with equal probability, and you start way to the very, very close to N, right? You start at N minus 1. Well, then it makes a lot of sense that the probability of reaching N before 0 would be extremely high, like N minus 1 over 1. So anyway, so now let's apply this idea to answer this problem, which is just a very straightforward application of this. So let's see, the probability that, what do we want to calculate? That the gambler quits a winner. What is the probability that, so in other words, gambler reaches, or I guess wins N before losing M dollars. Okay? Well, we can, this is very straightforward. This is the same thing as saying that this is probability of, say that we start at M, probability of winning N before going broke, given that we start at M. I'm just sort of translating it into the context of the gambler's ruin. So in this case, so I is equal to M, if we were to look at the formula. Capital N is equal to N plus M. And yeah, that's all we need. So this probability, and I guess P is not equal to 1/2. No, P is not necessarily equal to 1/2. So we get that this is equal to 1 minus Q over P to the M divided by 1 minus Q over P to the N plus M. This makes sense? Any questions? Okay. This gambler's ruin thing is a great application. It's used time and time again. So it's a good thing to know. Okay. For example, here. So this is a good exercise. It's a so we have a particle that moves among n plus 1 vertices. So we have sort of a cycle graph here. Vertices numbered 0, 1, 2, and all the way to n. And the particle moves clockwise with probability p and counterclockwise probability q. And given that it starts at state 0, call state 0, we want to, and so we start at 0, and we define t to be time when all states have been visited. We want to calculate what is the probability that we visit. Oops. Oh no. Oops. Sorry about that. T is the first time when we go back to 0. Okay, so we want to calculate the probability of visiting all the states before time t. So in other words, given that we start at state 0, we want to see what is the probability of going all the way around to state n before actually going back to state 0. So, and that could happen in two possible ways, right? We could either go clockwise in our first move, and then we would have to find a way to go from 1 all the way to n before going back to state 0. Or if we go counterclockwise, then we would have to find a way to go from n all the way to 1 before going back to 0. So, let's see. So now let's follow what I said just now and condition on what happens on the very first step. So let's call this event A. So this probability of A, given that we go clockwise, times probability of clockwise, plus probability of A, given that we go counterclockwise, let's say CC, times probability CC. Okay? Just to be consistent, let's call this C. Okay, so now what is probability of A given C? And how could we find a way to relate this to the gambler's ruin problem? Well, if we go clockwise, that means that, as I said earlier, we have to visit all the states from 1 to n before going back to 0. So if we were to relate this to kind of a wealth problem, then we would have our fortune would have to reach a a level n before we go broke type of thing. And that's how we will have visited all the states before we first go back to state 0. So okay, but now we're starting at state 1, right? So in our formula over there, I will be equal to 1. So we get the following formula. Does this make sense? So, since it does, can someone tell me what this would be? Following the same kind of logic as here? Exactly. Yeah. So the answer is exactly the same as the first one, but now you flip the Q and P's. But why is that?
Because Q is the probability that you're going to.
Yeah. Exactly. Because now the probability of winning is Q. Yeah. Right. So now the problem is done because, of course, probability C is P1 minus probability CC. So we can just plug in these expressions into this formula. Any questions? Okay. So let's do the last problem now. Problem 76. Okay, so we have a chessboard. So and we start in one of the four corners. So let's draw the chessboard here a little bit. 2, 3, 4, 5, 6, 7, 8. Okay, so now starting at one of the four corners, let's see. So we want to figure out what we call M11, so which is the mean time to go from square 1, 1 back to 1, 1. I think that's the notation, right? Yeah. Well, I guess it would be M 1 1 1 1. Okay. So, to do this problem, first of all, we need to, I don't know, I'm guessing you did this in class, right? The graphs. So we need to recognize that the chessboard is nothing else but an elaborate sort of graph, right? So if we look at this in terms of that each square is a vertex in the graph, and that if we have a knight, well, we can go from some square to some other square, or the vertices in the graph are connected only if a knight can go from one to the other. So let's view this. A graph where the vertices are the squares and two vertices are connected only if a knight can go to one from the other. And finally, let's also give each give weights to each arc. So this is the weight on edge ij. And let's just say that this is equal to 1 for all edges in our graph. And so then, and we also assume, I guess, that the knight, given on wherever he is on the chessboard, will visit each square he's able to visit with equal probability. So we also assume that so the probability of traversing edge ij is equal to wij divided by sum over all j of wij. So in this case, this definitely works because say that we're in the corner square here, we can go we have only two options. No, we have we have only two options. So here, say the probability that we go from 1 1 to 2 3 is 1/2, right? Because we're on two options, 1 over 2. So this works. And then we know from example, what is it? Example 432, that the stationary probability of being in a certain state is just the sum of all the edge weights emanating from that state divided by the sum of all the edge weights. So sum of inj over all inj of wij. So now P11 will be equal to 2 divided by this number here. So now we need to find what this number is. And to do that, we essentially just need to count a lot. So, for example, for these 4 squares here, we have how many possibilities? We have 2 for each one. So we have, so it's 4 times 2. Now let's see what we have. I think there are 16 squares. There's 6 possible. I think at the very center, so say these squares here. So from here we can go anywhere, right? So here we have 8 moves. So, and now we do this for kind of all the squares in the graph, and it's kind of tedious because you have to figure out, like for instance, these squares will have 4 options each, and so you just have to be careful counting things. But in the end, so 4 squares and 2 possible moves, or 8 squares with 3 possible moves. There are 20 squares, 4 possible moves, and there are 16 squares, 6 possible moves, and then you add these all up, and this becomes 336. And this is the sum over all I and j of wij. So there's nothing really, and the only kind of tricky thing is to make sure that you count correctly. And since it's only 8 by 8, it's not so hard to do, but it could be much harder. So then P11 would just be equal to 2 over 336, which is 1 over 168. And then we know that, I guess from remark, so from section so we have this. Oh, I hope the computer is not obscuring this. Maybe this. Let me see if. Okay, it's okay. So therefore, we get that mu m of 1, 1, 1, 1. So the average number of moves it takes us to go from a corner square back to a corner square will just be equal to 168. So, any questions? No? Okay. Thank you.